everything we've spoken about in this session has really focused on using drop jump tests. But are they the only method? And actually, there are limitations in there. If you think about, really, you have not actually had a direct assessment of force. If you think about what we've done, we've simply measured jump height, and we measured jump height over time. We've used height as our proxy indicator, as we do with counter movement and squat jumps, as our proxy indicator of power. What about if we could find a way of actually assessing the amount of force being produced? And that's where this notion of isoinertial force mass tests come from. Well, it comes, or the rationale for these comes from the assumption that typical human movements, particularly those in athletic performance, are characterized by, as again, acceleration and deceleration of a constant mass. Well, that makes sense, doesn't it? You know, the human is a constant mass, we accelerate and we decelerate. So there's nothing different there to what we've been learning. So when we're getting kind of an assessment of dynamic qualities of muscle, it may be more specific to measure the forces or torques that can be produced against a constant mass rather than at a constant velocity. And this is the notion of isoinertial. Now, we've covered isoinertial strength, so if you want to go and understand that a little bit more, worth going back to a previous session which is on the assessments of isometric and isoinertial strength. And that reflects the assessment involved using kind of constant mass, and then it's the differentiation between the deceleration and the accelerational forces. So here we can see this. So we've got a concentric force mass test. We do this with the squat bar, and you just have a simple load of 10 kilograms. And we ask them to start with a knee angle of around 110 degrees, and they jump as fast and as high as possible. It's a jump squat. And you do this off a force plate, and you record rate of force development, the peak force, and the vertical displacement. So that tells us how much force they can produce concentrically. Now comes the eccentric phase. The difference here is we're separating these two components out, and we're going to kind of, this kind of allows us then to separate out and understand the concentric power generation and the eccentric. It is different to a drop jump where you get the full stretch shortening cycle capability. Now what you do is you apply a resistance to the bar, which is 200% of body mass. The participant adopts the semi-squat position, knee angle of about 160 degrees. Now the bar is now positioned at shoulder height, and it's locked. So you have to do this on a Smith machine, but it has to be a magnetically controlled Smith machine. And what you then do is you just, with that, the participant is ready, and you just drop the bar. The participant then has to resist that falling bar. Remember, that's a heavy bar. So now they're resisting as this falling bar. It's a constant mass. Bang! It drops. They have to apply the braking force to stop them collapsing, the bar hitting the ground. So now we're braking. The muscle is under stretch. So the same thing applies. We record rate of force development, our peak force, and our vertical displacement. So what we have now is how quickly did we slow the bar down, and how much force was needed to slow the bar down. Under both, and that's under eccentric loading. Under concentric loading, how quickly did I accelerate the bar, and how much force was needed to accelerate the bar. I've got the stretch shortening capability, but I've just broken it down into two separate components. And you can see some data here. You can just see this is kind of a training intervention that's done this. And here we've got, for example, this is our eccentric. This is the bit we're interested in, our eccentric 200 force and rate of force development. And it just shows you the kind of effect it does respond to training, both in terms of the newtons per second, that's the rate of force development, and the amount of force that they are able to produce. So it does respond. It does mean that you have this as a measure which could be used by strength and conditioning coaches, therapists, and physiologists. It is, as you can probably understand, quite difficult. You need specialist equipment, and it's also quite dangerous, right? You've got a bar which is dropping. So you do need to be very conscious of that when working with this kind of test. And then I suppose the final part to think about is, well, okay, what about kind of repeatability? Well, don't worry about the constant loads. The concentric loads. I want you to focus on the eccentric. So here we've got eccentric 100, 130, 150. So that's relative percentage of body mass. And actually what we can see, although we were talking about 200% of body mass, you probably actually don't even need to go quite that high. This is from some data from Murphy and colleagues, and they're actually suggesting, actually, if you ever go to, to 150% of body mass compared to 100, there's barely any change in the amount of braking force that is needed. So actually, kind of efficacy, you can probably get away with using 100% of body mass rather than having to go much higher and still produce a valid measure of stretch shortening capability. And in fact, Murphy goes on to write this. The findings of the present study support the notion that the test should be as specific as possible to performance, particularly in relation to mass and contraction type. However, if a limited number of tests are to be performed, it would appear that the maximal forces produced during concentric 60% and eccentric 100% body mass tests may represent the best general measures of muscle